In this lecture 5, the molecular diffusion, that is Fick's law, will be discussed. So as you can see, the assumption, what is the first assumption we make? Assumption is that whole of the bulk fluid is not moving. So bulk fluid is not moving. We are only considering diffusion of the molecules. Diffusion of molecules. Okay, that means bulk fluid is not moving but is stationary. That means we have a small, cup and the whole stationary. This is all stationary. Only the diffusion is by molecules. So then, what is underlying principle? What is happening here? What is happening here is diffusion is through, or diffusion of the molecules is due to concentration gradient. So concentration gradient, how do I express concentration gradient? It is generally dC by dz or dx by dz. So the general Fick's law, which is written, is this form. J A Z star. Z is the what you call direction in which the molecule is moving. A is the component which is being transferred, and Z is the flux. Okay, so this is for a binary mixture of A and B. So there is a diffusion. So it is minus C small c dAB dxa by dz. Okay. Now this total C, what is this C? C is the total concentration of A and B because we are considering a diffusion in a mixture A and B. That means A is diffusing through, or B, diffusion of A and B. C is the concentration, Xa is the mole fraction of A. Xa, if I say mole fraction of A in the mixture, if C is constant here, so now the other, if C is constant, so what we write? If C is constant, we have an equation that means C A by C. What is CA by C? XA. So I can write this as CA is equal to C into XA. So in this equation, what I can take this C, I can take inside this derivative function. So this becomes JAZ star is equal to minus DAB D into CXA by DZ. So, but C into XA is nothing but CA. So ultimately this equation converts, and here it is written like this. So this equation is commonly used one in many, that means any molecular diffusion processes. Okay, so this is the Fick's law equation. Now suppose the second one is when the fluid is flowing outside a, see, this is a, I have taken a diagram here. This is a pipeline surface and this is the pipeline surface, and there is one more pipeline inside. The fluid is flowing annulus, see in the annulus. Okay, that means this is the surface, this is the surface, and fluid is a blue color. When the fluid is flowing outside a solid surface in forced convection motion, that means suppose say through pump, we have a pump here, and then through the pump, this fluid is being sent. Okay, we can express the rate of convective mass transfer from surface to the fluid. See, this is the surface. Let me take another color here. Yeah, so this is the surface to the fluid. Okay, so convective mass transfer from surface to the fluid, or it can happen another way also. That means from the fluid to the surface also. So this can be this surface or this can be this surface, nothing problem. It is given as, if I say convective, I should write Na, not Ja. So it is small kc into Cl1 minus Cli. So Kc is one term. It is known as mass transfer coefficient. The units are meter per second. And it depends upon, it is actually, mass transfer coefficient depends, or it's a function of system geometry and fluid properties and the flow velocity. There are three things here. It is a function of mass transfer quotient is a function of system geometry, fluid properties. Number one is system geometry, fluid properties, flow velocities. So mass transfer quotient. We have another term. We have another term called CLI, and bulk fluid concentration. Bulk fluid one. Okay, let us, because representing this one as bulk fluid concentration in kg moles of A per meter cube. So generally concentration units are what? Moles per volume. I think you should remember this, right? The bulk fluid concentration is given as kg moles of which component? A per meter cube. Then what is CLI? Let me rub this. It is not looking good here. Yeah. So let me write it again. So this is CL1. Okay. So let me, yeah. Now if I say CLI, it is actually telling me that is just here, this location. Solid and the liquid boundary, I can say. Concentration in the fluid. See, whenever we say concentration, we don't say concentration of solid, right? We say concentration of the component A in the fluid next to the surface of the fluid. Next to the surface of the fluid. I think you are able to get what I'm saying. The CLI. So I we represent just next to here, here. Okay. So that's way, that means we can actually define convective mass transfer, convective mass transfer coefficient. But we have defined previously also driving force divided by the resistance. So if I say what is driving force here, CLI minus, sorry, CL1 minus CLI is the driving force divided by 1 by Kc. If I say this is nothing but NAC. So driving force by resistance is flux. As if current is equal to voltage by resistance, I can write this also like this. Okay. We'll meet in the next session. This is session 5, wherein we have introduced Fick's law or Fick's law of mass transfer, Fick's law equation.